Good morning. Assignment 5 Coordinate Vector. This is the last assignment of this course and it is a very simple and small concept on coordinate vector. The definition is let B is equal to V1, V2, V3 up to Vn be an ordered basis for vector space V over F and a vector V is belonging to V. And if this vector V is written as a linear combinations with this ordered basis, that is having the scalars alpha 1, alpha 2, alpha 3, alpha n, that belongs to F. So the linear combination is alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3 up to alpha n Vn. Then the vector, this is the how you denote the coordinate vector V, the coordinate vector of V relative to the ordered basis B. So this is equal to, just write down these scalars as alpha 1, alpha 2, alpha 3 up to alpha n. And then this vector is called the coordinate vector or matrix of V relative to the ordered basis B. So this is your coordinate vector of this V that is belonging to the vector space V relative to the given ordered basis V1, V2, V3 up to Vn. And this is your actually a matrix that is n by 1, having the n rows and 1 column only. So that is why it's written or matrix. The scalars alpha 1, alpha 2, alpha 3 up to alpha n are called the coordinates of vector V relative to the ordered basis B. So these are known as the coordinates. Right? Alright, let's move on to the examples that makes more clear to you. The example 1 is, find the coordinate vector of V which is given to be 2, 3 relative to the ordered basis B as 2, 1 and 1, negative 1 of R2, that is the 2 dimension. So the vector V is given to us. We have to find out the coordinate vector relative to the given basis, that is the ordered basis. So first let's write down this vector V which is belonging to the vector space V as the linear combinations of these ordered bases, and I'm taking the scalars to be alpha and beta for this. So alpha 2, 1, I'm writing the linear combinations and beta as 1, negative 1. And vector V is given to be us as 2, 3, so write down here 2, 3 for V. So this is equal to alpha 2, 1 plus beta 1, negative 1. So this is further equal to, if you add them, you get 2 alpha from here plus beta. So this is 2 alpha plus beta, and then alpha plus negative 1 into V, that is negative beta. So that is alpha minus beta. Right? So now equating the first element, you get 2 alpha plus beta is equal to 2. Then equating the second one, you get alpha minus beta is equal to 3. We have to calculate the values of alpha and beta, right? That is why from here we can get the coordinates and then we can write our coordinate vector. So adding, we get, if I add these two, I get 3 alpha is equal to, alright, let me write here first. So by adding, I get 3 alpha is equal to 5, which implies alpha is coming out to be 5 over 3. And from here, from the second equation, I can put the value of alpha here. I get the value of beta as alpha minus 3, which is equal to 5 over 3 minus 3. That is equal to negative 4 over 3. Right? So now putting these values of alpha, beta back to this equation, first one, you get V is equal to 5 over 3 to 1 plus negative 4 by 3, 1, negative 1. Right? So these are your coordinates. So writing the coordinate vector relative to the ordered basis B. So this is your coordinate vector just write down these scalars, the values of these alpha beta over here. That is 5 by 3, negative 4 over 3. Yes. So these are actually your coordinates of vector v with relative to the ordered basis b, and this complete vector is your coordinate vector having the coordinates 5 by 3 and minus 4 by 3, right? So this is your required coordinate vector of v relative to the ordered basis b, right? So let's take up the second example. Let V be the vector space of 2 by 2 matrices over R. Find the coordinate vector of the matrix A belonging to V relative to the given these ordered bases, where A is given to be this matrix. So I have to write first A to be equal to the linear combinations of these ordered bases. I have already written this. Writing the matrix A, which is 2, 3, 4, minus 7. This is equal to, now if I add these, I get, from here I get alpha, from here I get 0 because beta into 0 is 0, then gamma into 1 is gamma, and delta into 1 is delta. So I get my first element to be alpha plus gamma plus delta. Then alpha, negative beta, negative gamma, and here 0. Then is alpha plus beta 0, 0. So this is sum of alpha plus beta. And this is then alpha because here also 0, this is 0, this is 0. Now if I compare these, I get alpha plus gamma plus delta to be equal to 2. And alpha minus beta minus gamma is equal to 3. Alpha plus beta is equal to 4. And alpha, finally, I am having negative 7. So very easily we can find out the values of alpha, beta, gamma, delta from these four equations. Alpha is already negative 7. If you put the value of alpha in the above equation, you get beta, that is 4 minus alpha, 4 minus negative 7, that is 11. And then putting the values of alpha, beta in the second equation, you can get the value of gamma, which is coming out to be minus 21. And then you get your delta to be as 30. So we have find out the values of alpha, beta, gamma, delta. Put these values in this equation 1. And you will get your result as this. And now you can write out the coordinate vector of A relative to the ordered basis B. Just write out the values of alpha, beta, gamma, that is negative 7, 11, negative 21 and 30. So this is a required coordinate vector. Third one is, let V be the vector space of all real polynomials of degree less than equal to 2. Together with the 0 polynomial over R, find the coordinate vector of the polynomial fx equal to 3x squared plus 4x plus 6 that belongs to V relative to the ordered basis given to be as 1, 1 plus x, 1 plus x plus x squared. So fx is now in the polynomial form, just writing the linear combinations with the ordered basis and taking again the scalars to be alpha, beta, gamma. So writing alpha into 1, then beta 1 plus x, then gamma as 1 plus x squared. Putting the value of fx, that is given to be 3x squared plus 4x plus 6. This is equal to, now because I'm having first 3x squared, that is with x squared. So let me also write from here the first term to be in x squared. So this is gamma x squared. And then the term with x, that is from here I get beta x from here plus gamma x. So this is beta plus gamma x. And then writing the remaining constants to be as alpha plus beta plus gamma finally. And now just equating these two, I get gamma as equal to 3, and then beta plus gamma is equal to 4, and alpha plus beta plus gamma is equal to 6. Now already I know gamma to be as 3, so put the value of gamma over here, you get beta as 4 minus gamma, that is 4 minus 3, 1. So from here I get beta to be equal to 1, and from here I can get my alpha, that is equal to negative of beta plus gamma. From the second equation I know this is 4, so this is negative 4. No, it is 2. Sorry. Beta plus gamma as 4, alpha plus beta gamma as 6, and gamma is 3, beta is 4 minus 3, 1, and alpha plus beta is 4, and gamma, beta plus gamma is 4, so alpha is equal to 6 minus beta plus gamma, that is equal to 6 minus 4, which is equal to 2. Excuse me, I'm very sorry for this. So alpha coming out to be 2. Substituting the values in 1, I've already substituted. So the required coordinates vector of fx relative to the basis b is, this is your coordinate vector of fx relative to the basis b is equal to, writing the values alpha, beta, gamma, that is 2, 1, 3. 2, 1, 3. This is your required coordinate vector. So this is how we can find out the coordinate vectors of a given vector with relative to the ordered bases that are also given to us. So here ends up the part 2 of the linear algebra, and I will be starting the new part of linear algebra, having the content row space and row rank of a matrix. That will be your third part of the linear algebra. Thank you for watching this course, and God bless you all. Have a very nice and blessed day. Thank you so much.